it structural
It
costs?
was to go by the rules. To meet the rules.
Well, let's just act like we were originally going with the rules, but we had another reason for doing it.
Okay.
Or I could say to
lower weight and
let's say we optimize by removing the cross
And
member
connections.
and reducing the rest of the cross members down to a single beam to apply
you don't have
the
to do
rules
that.
and to lower the
don't want
weight.
You don't have to do that.
Please don't record us. No.
here we have intermediate loading on member BC. So to build the load vector, okay, you need to find the loads at point B, okay, due to this uniform load, okay. So to do this, this is member B. You have 3 kips per foot. The length of the member is 20 feet. So the equivalent for 3, this is 3 multiplied by 20. So that's 60 divided by 2. So you have 30 here, 30 here. So you can remove this load and put an equivalent load here. And for the moment, you find the fixed end moments, WL squared divided by 12. And WL squared divided by 12 from the table for the fixed end moments, just the opposite of it, okay? So that's the action here. This is counterclockwise, so that's positive. This is clockwise, so that's negative, okay? So for the load vector, that's what you have over here. For the first 3 degrees of freedom, 1, 2, and 3, there is no horizontal force, so that's 0. For the vertical force, you have this force over here, the negative 30. And then for the moment, you have negative 1200 kips inch. So those are the load vector at 1, 2, and 3. For the 4th to the 9th, you don't know how much are those, okay? Because there are reactions there, okay? You don't know the magnitude of those loads, okay? And then for the member stiffness matrix, we did this last time. For member 1, you need to find the cosine and the sine of that member, because the member stiffness matrix is a function of the cosine and the sine. You need to find EA over L, 12 EI divided by L cubed, 6 EI divided by L squared, 4 EI divided by L, 2 EI divided by L, and then substitute those into the matrix, okay? The stiffness matrix for the element. So that's the stiffness matrix for the element that we had for the frame. You don't need to memorize it. I will give you that on the test, okay? So you just need to substitute the numbers for each member, okay? Once you find this, you do the same. So those are K1, okay? And then for member 2, okay? Member 2 starts from node 2 and ends at node 3. So the angle theta is 0, okay? So theta is 0. Again, you find EA over L, 12 EI divided by L cubed, 6 EI divided by L squared, 2 EI divided by L, 4 EI divided by L, and substitute those numbers into the matrix. Cosine theta is 1, because theta is 0. Sine theta is 0. So you substitute those numbers and you get K2. That's K2, okay, for member 2. And then from those, okay, I'm just going to go quick on this step because you know how to do this. K, the overall stiffness matrix, you build this from mapping the elements, okay, from K1 and K2 from each member. You have here 9 degrees of freedom. You label those here, and you start, mapping the elements to build the overall stiffness matrix. We did this many times for the beam. We did it many times for the truss, so it's the same, okay? You just map the members, the elements here. I just found those elements and those elements, okay? I don't need what's here and what's here, so I didn't waste my time calculating those, okay? You too, you don't need to waste your time on the test calculating each and every element in the stiffness matrix, just what you need over here, okay? And then you solve, again, I'm going fast here because we did this is exactly the same as we did in the beams and the trusses, okay? Now you solve the stiffness matrix P equal KU, you solve the first 3 equations, okay? So you have P, those P is equal to K, which is going to be 3 by 3, the first part that we had here. This first part, multiplied by the unknown displacements. So you solve for the unknown displacements. So those are the unknown displacements, UXB, UYB, theta B, the displacements at point B. That was the first part that you needed to find in this question. And then to find the reactions, what you do, you substitute into the next 6 equations. And you add any effect for the intermediate loading as we did in the beams. Okay? So it's the same here. So those are B4, 5, 6, 7, 8, 9 from substituting into the next 6 equations. Okay? Once you find those are not the reactions. You have to add the effect from the intermediate loading as we did in the beam. Okay? So this step is repeated. Okay? So here I'm adding those from the intermediate loading, the opposite of what we had. So for the intermediate loading, as you see here, only at point C, okay, there was an effect for the intermediate loading. Where's that? You see here, at point C, those were the actions, so you have to add them as the actions, so you can add them in the opposite direction. So instead of negative 30, that's going to be 30. Instead of 1200, it's going to be negative 1200. So that's what I'm adding here for the force in the y direction and the moment. 30 and negative 1200 for CY and MC. Okay? Those are the effect of the intermediate loading. I have to add them to those forces to find the reactions. So now those are the reactions. Okay? Once you solve for the reaction, the thing that I want to do it clearly here, okay, is calculating the member loads. What is the member load? The internal forces here. So in this problem, okay, this is similar to what we did in the truss, but I want to do it again here for the beams or the frames, okay, slowly so that you can understand this. So we calculated the reactions. We calculated the rotation at point B. Now we're required to calculate the internal forces at B. How much are the internal forces at point B? So please focus now. Everything that we did so far is a repetition of what we did in the beams and frames, okay? But this part here, I want that to be clear to you. The internal forces here at point B, okay? The moment, the shear force, okay? And the normal force. To find the internal forces, you have to break the structure over here, right? Once you break the structure into two parts, you're going to have three forces here and three forces here, right? The moment is the same. If you have a vertical force here, that would cause shear here, right? If you have a horizontal force, that would cause normal force here, right? If you have a vertical force here, does this cause shear? No. Actually, the shear is a force perpendicular to that member, right? The normal force in this member is perpendicular to that, is in the direction of member A, right? It's not the vertical and the horizontal force, okay? So how to find those internal forces? As you see here, as we said, for this member, it's horizontal, so the internal forces, the shear is vertical, the normal force is horizontal. Here, this member is inclined, so the shear force is perpendicular to its direction, and the normal force is in the direction of the member, right? What does this mean? It means that the internal forces, okay, are something, or it's a local property, right? It depends on the direction of the member. It's not the vertical and the horizontal force. It's the force perpendicular to the direction of the member and in the direction of the member. So it is the local forces, okay? So to find the internal forces, you actually would find them from the equation P equal KU, okay? But you have to use the equation in the local direction, not in the global direction, for each of those members separately. Okay? Is this point clear?
Not yet.
Are you talking about using tree? Like cosine and sine?
No. No, we're using P, the forces, the internal forces, P. The internal forces are forces, right? P equals KU. That's the only thing that we know here, right? That we use, the stiffness equation, P equal KU. What P are you looking for? You're looking for local forces. So you're using P local equals K local, U local, okay? Everything is in the local direction to find the local forces, okay? In the direction of the member itself, okay? So how does this look like? We wrote this before here. That was the local stiffness matrix, okay? For a member. So that's what we're going to use. So that's P, or that's K local, okay? We need to find P local. So what's U local, okay? How to find U local? U local, okay? Here is the T matrix multiplied by U, the transformation matrix multiplied by U. So that's what we want to do. It's so simple, but, you know, would take some calculations. So to find the internal forces, this is member 2. I have those internal forces, 1, 2, 3, and this is 7, 8, 9. Okay? If I break the member like this. Those forces at point P are the at point B are the internal forces here. Okay? So how to find this? Just write P equal KU in the local direction. So P1, 2, 3, 7, 8, 9 is equal to K in the local direction. This is K in the local direction for the member. Multiplied by U. What are U? It's 1, 2, 3. Those, we just found those, right? And fortunately, this member is oriented with the X axis, okay? So the local direction is the global direction for this member, right? So the displacement that we found in the first step is the same in the local direction. I don't have to transform them. And the displacements over here are zeros, okay? Plus the effect of the intermediate loading, okay? So I put here the effect of the intermediate loading not as an action, but the reaction. So I'm just putting it in an opposite direction to what we found initially. Those are the actions there, okay? And then just solving those. Solve this. Here, those are numbers. Everything, you can just do the multiplication. P1 is going to be this column, this row, multiplied by this column, plus this value. So that's P1, okay? That's P1 represents what? The normal force here. P2 is the shear force. P3 is the bending moment, okay? So solving this, those are the forces that we found. This is the normal force. It's compression, 24.7 positive, so that's positive shear. The moment is 398 kips inch, okay? Dividing by 12, you can find it in kips feet, okay? That's the moment, okay? Now, to do the same thing for member 1, those are the internal forces, B4, 5, 6, B1, 2, 3. But B1, 2, and 3 are not the same ones as in member 1. Why? Because they are in a different direction. They are in the local direction of the member. Okay? So again, write the equation in the local direction, B4, 5, 6, 1, 2, 3. Why did I put it in that way? Because you have to start with the start of the member. That's the start of the member. That's the end of the member. So the start first, okay? The normal, and then the shear force, and then the moment. B4, 5, 6, B4, 5, 6, and then B1, 2, 3. B1, 2, 3 is equal to K in the local direction multiplied by U. U are the 3 displacements here, which are equal to 0. And then the 3 displacements here at point B, but in the local direction of the member. Those are the local displacements. So how can I find U1, 2, 3? It's T multiplied by U global. Okay? So this is K over here. I just substituted the number of E, I, and L. Okay? And then to find U, this U is equal to T, the transpose matrix, okay, the transformation matrix multiplied by U global. U global, I know them. So this is the transformation matrix, which is cosine, sine, negative sine, cosine, 0, 0, 0, 1, and then the same here, okay? Multiplied by the displacement, the U global, the first 3 points or 3 degrees of freedom were zeros, and then those are the displacement that we found at point B in the global direction, okay? Just solving this, you get the internal forces here. As you see, the moment is the same at point B. It's the same as we did for the first member. It's just a negative sign because they're equal and opposite in direction. But the normal force and the shear are not the same. Those are the normal and the shear force. Okay?
Not looking pretty. Not right.
Which part did you get?
I mean, it somewhat makes a little sense. Yeah, it's slow.
Okay, so the first part is straightforward, right? Calculating the displacements, the reactions. There is no problem with that, right? Does anyone have a problem with calculating the internal, the reactions or the displacements? No. Okay, that's great. The only step that we took forward is calculating the internal forces. To find the internal forces, the summary, the most important thing for calculating the internal forces, you have to find the internal forces using the local equation. Just P equals KU. If you want to find the internal forces in member 1, so apply this equation to member 1. P are 6 forces. 3 forces at the start, 3 internal forces at the end of the member, right? Equals K. Just substitute K local. Multiplied by U. You already know U, but in the global direction. You only have to transform it from the global direction to the local direction. Okay? How can you do this? Simply, U local is equal to T, the transformation matrix, which you don't have to memorize. You will be given that on the test. Okay? It's C, S, minus S, negative S, C, and then 0, 0, 1. It's so easy. Okay? Multiply those, you get the U in the local direction. Just do the multiplication, it will give you the internal forces. If there is intermediate loading in the member, you just have to add the effect of the intermediate loading to those internal forces as a reaction, not as an action. Yes?
So in your local equation, P equals KU,
Yeah.
you transform the U in the global direction, right?
When you calculated U in the first step, the step that you said you understand, you calculated U in the global direction. Now, you need to find the internal forces. The internal forces are in the local direction. So you need to transform those U's that you found from the global direction to the local direction.
And that's
Okay.
the equation.
That's
T
T times U global. Okay?
So pretty much we're just doing cosine and sine to everything inside of that matrix.
Yes. The transformation matrix is only C as cosine and sine. Any question? No question. Okay.
Can our final be a take-home question?
So for the final exam, you're going to have problems for the matrix structure analysis. For B is frames and trusses. Okay. I might just give you 2 problems or 3 next. Okay. Beams, no beams. Frames and trusses. Frames and trusses. The final exam is going to be on, according to the university schedule, like
December 10th.
Monday, right here, from 8 to 10. Okay. The last homework, I will assign the last homework on the frames and process today. Okay. And you can submit this by Wednesday of next week. Okay. Any question? Okay. So now your turn.
Don't get that.
Like, I'm glad we.
Okay. Just get your presentation. I guess you already put it, but please put it again, because.
Yeah, let's get it over with.
Uh.
You may tell Adam and Tristan.
Yeah. Do you want to log in your account?
How do y'all feel about seeing how many
No, I got it right here.
How many how do y'all feel about seeing how many slides you have and just split it up? Okay, so you want to do 5 apiece? No,
We've already signed.
I know, but I've already forgot, and I feel like there's going to be confusion.
I know what I'm doing. Stay over here.
I would say we could just do 4 apiece. Just go down the
There's
line.
more than
First
20.
one.
There's 21.
I know, the last one can do 5.
But I already know what I'm going to do.
Well, he's doing the last one anyhow. Do you want this moved over to his folder?
Are you an
Do you want this moved over to your folder?
See,
Do you want our stuff moved over to a folder of yours or anything?
Then you want
No,
to
no,
do
no
policy
problem.
design.
But just
I'll just do the whole optimization.
email your. So for
Yeah,
both
we do
groups,
policy.
please
And let
email
him
me
do
your
policy design.
presentation, okay?
Okay.
So do you want me to just do all?
For both groups, one of you have to each group email me your presentation, okay?
That software would not allow us.
There is no credit unless you email it.
You want the new stat file as well?
I need the stat file for your final selection. Just one
It needs to start.
design for the design that you selected as a group.
Stat file.
Yeah, the stat file.
Oh, okay. I have it, but that means you have it too.
No, because I thought you
It says new.
All right, let's
do we, are we doing that first or not?
No, later.
while we're doing optimizations.
All right, this is our final design. The group is composed of the following members.
This is my individual bridge design. It had 90 connections, weighed approximately 517 pounds, and it was right at the 30-minute mark. And this is the front view of my individual bridge.
This is my individual bridge design. I think it had 44 connections, and it took somewhere around 15 minutes to build. It weighed too much, it's like 600 pounds. Here's the front view, and
this is my individual bridge design. It approximately weighed 250 pounds, and it consisted of it was 48 connections. It performed less than what I wanted it to, therefore it was not chosen for the final design.
Here's my bridge design. I chose to go with all one style of members, which was hollow tubes. Everything was good. Weight was 236. Length, everything matched up, and everything as far as the members went matched up. But my deflection was my aggregate deflection was higher, so we chose not to go with this one. There's the front view.
We actually chose Matthews Warren bridge with verticals. It has equilateral triangles to spread out the loads applied onto the bridge and offer more stiffness.
We added verticals for the longer spans to provide extra strength.
another advantage of this design was there's only 54 connections and 42 members within the bridge. So along with it was mostly male to female connections throughout the thing to make it easier to put together.
It was lighter in weight than his original design by 75 pounds, and that made up for a lot of our costs in the end.
And with the optimizations that we did, we were able to cut time by reducing the amount of connections, and we also reduced took it down a builder, so we could do it with one less builder, and we reduced the time from 30 minutes to 18 minutes. This is the final bridge overall view. Originally, it did not look like this. There was a lot of optimizations that went into this. The overall length I used was 23 feet, and I tried to get to the bare minimum of height. So my footings were 13 inches, and then from there to the top of my loading rails was the other 7 inch or 6 inches to make it exactly the bare minimum 1 foot 7 inches. I tried to do the bare minimum width as well at 2.67 feet, and then obviously the size.
The optimizations we made is we added members to decrease the deflection. We took away members to lower the weight, and then also with the members that we added, it helped with the lateral deflection. Also, we put braces around the footing to also help with the lateral deflection. We had ideas for aesthetics on the bridge to make it look better, and Also, as Tim said, we reduced the members, the builders that we were going to use, and with the reduced amount of members, we were able to help with cost and time. This is the first optimization we had. This is before we optimized the loading rails, and then this is after we optimized them. We have them shown as 1.5 inches by 1.5 inches to represent what they're supposed to be in stab, because it cannot do what we needed it to do. And these are the results of it after we made the optimization of our deflections and sway and also weight. We also removed crossing members from the center of the bridge, which lowered the weight. We removed the first one and the line of them we have, but the other ones we decreased. We removed the top sections of them, which we still have the crossing members, but they aren't as wide as they were in height. And that is okay. Yeah. We also removed the footing brace of it. We added a brace in the middle of it, in the middle of each footing for extra support and strength. And those are the results of it after we made that optimization.
As far as aesthetics go, we wanted to keep it simple and do a theme for Arkansas State, just to keep it looking good and everything else. The more simple you could go, the better time you would have and everything else. So that's what we decided to do.
Okay, so you can see on, like I said earlier, our time for construction before we started, optimizing was 30 minutes. And so you can see the numbers there. And what we were trying to do was reduce the number of connections for faster build time, and so we could also cut a builder, because that would also help a lot with cost. So you can see here, after optimization, we were able to get it down to 18 minutes and 54 connections, and only using 5 builders, which cut our cost pretty significantly.
This is the actual construction of the bridge. We decided to do 5 builders, 3 builders on the long side because it is going to be the heavier end. 2 people being the runner, going to carry the members and actually building, while one's holding it, making sure the footings stay within the parameters and that it stays up, because the bridge can never fall and hit the ground. On the short side, we just did the 2 builders, one being the carrier and actually building it, while the other one holds it stable. You'll go to the next slide. So the construction of our bridge, both sides, this is the long side because the offset of the river is closer to the left. Each side will start from the footings and start doing the stringers. The long side will have 2 extra sections. That's why we kept an extra builder on that. And then they'll meet in the middle over the river.
So, as you can see, the best overall performance bridge was chosen. So compared to everybody else's, my beginning design, the cost was the second lowest compared to everybody else's, along with my aggregate deflection. Some was right in the middle ground, so it was kind of the average of all of our designs. We did several optimizations that significantly helped it a lot throughout the design process. The costs were recalculated with the optimizations, and as you can see in the previous slides, that it drastically changed the beginning costs from whenever I first submitted it to after we changed a lot of things. And then the main thing to get this for us to build it fast is just the practice.
Any questions? Thank you.
Questions? Okay, so I don't have a question, but I have a comment. So even for your design,
Yes, sir.
it was, I guess it was one of the good ones, but you you think that the cost was high because the way you calculated the aggregate deflection, I wrote this for you in your report. The way you calculated the aggregate deflection was wrong.
Okay.
If you calculate the aggregate deflection correctly, maybe your design might
It would have
be
been the one to use.
the better design. The way you calculated the aggregate deflection, you added the deflection for all 6 load cases. No, this is
Right.
not the way you
Yeah, we decided last night, or I found out last night that it was for each case instead of all. And
You have to do it, for each case, and then you select the worst case scenario.
yeah.
So if you did this, I believe your design would have been maybe lower cost. Okay. And for Sarah, your design is good, but I don't know why you weren't able to.
It was
get
the weight. It was the weight.
down. I don't know why you have it 700 and something. I remember we talked about you have 2 plates right in the middle between the 2 members, right? And we said you don't need actually those 2 plates, right, all over throughout the length of the bridge. So you actually can have this as a perforated plate. You have holes in it, large holes. That would decrease the weight. Okay. Also, you could have decreased the weight by using smaller members for the diagonal those members. Also using smaller members, because your design is based on the idea that you're increasing the moment of inertia by having bigger depth, right? So you're actually building each member as 2 members on top of each other. So you can decrease the weight as much as you can, because your moment of inertia doesn't depend on the weight of the member or the area in the member. Your actually moment of inertia is based on the depth, right? So I believe you could have, get the weight way down than 700. Yeah, I believe like yours could have been maybe in the order of 250 or 300 pounds if you wanted by, using this perforated plates, but you had to do the calculations by hand because you cannot.
You can't represent it instead.
But you can do it by hand. So that would decrease because you have those plates throughout the length of the bridge. You actually need them at the connections only to connect the 2 members together. So I believe if you did this, your design would also be a good design, competitive one. But you weren't able to do that. But it was a good one. So any question?
Did you divide these up between truss and no truss? Does it seem like no, you have no truss?
None of us had a trust.
No, it's not trust.
Others.
All right. Thank you, guys.
Okay, so thank you. Guys, you have to send me your presentation, huh? If you don't send the presentation, you don't get credit.
You want the presentation and the stat file?
The presentation and the stat file and the PDF or Word file of your final presentation.
Where you plug this shit
We
in?
turned it in.
Yeah.
You want a PDF of it as well?
PDF or yeah.
I got the PDF, I got translation.
I know you.
I think this is it.
I just needed the new pictures.
I'm gonna click.
Here.
Yep.
We did a lot.
All right, so our group was me, Brooke, Taylor, Bryan, Paige, and Sean. And this is what our presentation is going to be over today. So my initial design was just a simple truss on rectangle prism members for the stringers, the cross members, and for the footings. And I had secondary bars in between all the members, or all the rectangular prism members, but the stringers didn't really meet the specs exactly, and the deflection was a little bit too high, and it weighed 676 pounds with 80 connections, and it took like 45 minutes to build. But it was just not the best design, so we didn't end up picking it.
This is my design. I did a hip truss. It wasn't chosen because the members I chose, the weight was really heavy. That helped in the deflection. The deflection was 0, but I mean, it was well over the weight it needed to be. And there was approximately 120 connections, so it's going to take a lot of time to build.
This is my design. It fit the template perfectly, and it was just a simple one truss, but it ended up weighing about 685 pounds, so that was why it wasn't chosen mainly. Oh,
For my bridge?
I forgot one thing. And then I had 46 connections, so yeah, that was one little thing.
For my bridge, my truss originally spanned the whole length of the bridge, but I realized as I shrunk the truss, it helped with my deflections. And when I added I did have just single cross members across the truss, and then when I added the X bracing, it stiffened it that much more. And my deflections were a little over an inch, and my weight was 239 pounds.
So this is my original design, and I went with the truss also. I just used basic hollow members all the way through it, and it wasn't picked because it was way too heavy. It was like 1,000 pounds.
All right, so this is my individual design. It's also a truss. It's relatively simple in the fact that the stringer is also the main beam. It's not a separate thing that you build later. Meets all the specs. And then you'll learn more about optimizations and members and connections later. So we actually decided to go with this one. Because it was the lightest bridge out of all of them, it had some of the lowest deflections, aesthetically pleasing, and then it's fairly simple to put together and had a good cost, a good low cost. So this is the east end, where you've got the offset footing. That's good. The north end, and then the south end, 266 inches, so 38-inch sections. And that's the top view.
So for the optimizations, what we did was originally the bridge wasn't the smallest distance apart it could be, so we brought it in one side in 3 inches to kind of minimize that, and it helped bring down the weight a little bit. And then we didn't account for the center line dimensions at first because Dad draws to the middle of the member, so we accounted for the center line dimensions, and with that we had to lift the entire bridge up 1 inch. So that added a little bit of weight, but we accounted for that when we brought the side in 3 inches. With that, we also shortened the cross members, and then we changed the footing from a solid tube to hollow tubing, which helped bring down the weight as well. And then on the top cross members, instead of having an extra connection, we put 2 4-inch members on both sides of those cross members and attached it to the outer sides, and they'd be welded together rather than connected.
So we put nodes at every point where they're supposed to measure the deflections at, and these were our aggregate deflections, and our max aggregate deflection was 0.554 inches, which we thought was pretty good. And then our max side sway was 0.084 inches, which was also pretty good compared to the rest of the bridges.
And these are the individual members. The inside footings and the end footings were all just little square tubes or hollow tubes. And for the cross beams, we had the hollow tubes or square tubes, and the secondary elements, as you can see, are little circle hollow tubes. And the girders are about the same. And the truss members are also hollow tubes, and these are the connections for the truss to the girder, which are the hollow tubes, of course. And for the footings, the square parts are 1 inch by 1 inch with thickness of 0.140625. And the truss members were circular, 1 inch diameter with thickness of 0.0625. And the cross beams for the square, they were 1 inch by 1 inch with 0.0625 inch thickness. And the circular secondary members were the little circle diameter, half-inch diameter with thickness of 0.0625. And the girders had a little higher thickness than the beam members with 0.140625. And the little circle members in between had a thickness of 0.0625. Yeah, they were all about the same thickness.
Okay, we had 70 connections completely. Male, female connections, nut and bolt connections, and 158 members.
The construction staff required 6 members altogether, 2 teams of 3, and each unit will consist of a runner, hammer, and joiner. We're going to start by assembling the base, footings, and everyone else. And then each unit will assemble their side of the stringer, and they'll connect the sides in the middle as they go, similar to the other group. And the process will be repeated with the south stringer. And both the north and south truss will be assembled simultaneously, meet in the middle. And the team performs check connections and returns to start.
So if y'all need anything clarified, I can do my best to
Got 2 questions.
do it. Yeah.
First one is, in your logo, how do your cross members come together?
It's actually going to have, if you go back to the member slide, if you can.
Are these?
So, here, go back up one. This one is actually going to have, what I had in mind is going to have a flat piece of metal, and it's going to have a couple holes in it, and then I'm going to have some holes drilled in my stringers, and so they're just going to connect via hinge. So you'll have, like 2 flat plates right here. But I didn't know how to represent that instead. Do what?
They want to interfere with the connection.
No.
How much is the overall cost?
Just under $10 million.
Yeah, 9 million something.
$9,825,000.
I think that was our highest cost.
I have this on the presentation.
It's in our.
Yeah, it's I guess we're.
No, but I can tell you if you want to know.
Okay.
The lowest cost would have been 9.2 roughly, and the highest was 9.8 roughly. But they're all of our lows. They're lows.
As you can tell.
How long are your members on your truss? That go up?
You talking about these guys?
Yeah, each one of those.
Yeah, so another thing, these little brackets right here will have a male connection, so that'll give me a little extra leeway. But they should meet specs with that little extra male connection. You get what I'm saying?
Yeah.
From that, I guess.
Because I've got basically 4 inches of male connection that I can add on to that. And I think like the longest one of those that we're talking about was like 41 inches long or something. So do the math, that works out.
Usually you've gone higher with your truss there than you have to for template. Is it just to get more, keep an arc shape and get more cross members on it, or is there another reason?
Optimization. Like
honestly remember exactly why I went with the height that I went with, but I was, basically looking off that template and doing my best to put together. So.
I don't think there was a reason, but I don't think we changed it because it worked and it didn't really affect anything. I mean, I guess if you did change it in the long run, it could possibly make it lighter for better score.
Yeah, it may be better if we had more of those crossovers.
Yeah, I think it helped with the deflection.
Anything else connection-wise? We'll clarify.
I think we already did.
That's yours.
I go to bed.
Yeah.
You still have time.
Drew, you got your flash drive on your keychain.
Download it.
Let's go.
Still have 30 minutes. So those guys in their senior design project, they also worked on the steam pitch design. So they presented that yesterday, so I will ask them to present it today as well.
Right there.
Where? You wanted to go?
You almost heard me get on the map here.
All right, we gonna do it again. All right, we'll just Austin had preliminary design. You talk about yours, I'll talk about mine.
What was your least cost? The
It's in
Just
here.
over 8 million.
8?
I have to check. But that was with we did 6 builders in our equation.
Okay.
So we're planning on using 4 in the competition. So I mean that'll go down a little bit. But
Well, we didn't really plan on giving this talk today, but here we are. If you were in our presentation yesterday, it'll pretty much be the same stuff you said there. So we took this as a senior design project in addition to you guys having it here, so got an extra design out of it this year. I don't think it's ever been done senior design here before, but us three and also Austin Petty were part of the group that did that. He's not here today.
introduction, manages problem statement, constraint criteria, brainstorming, our initial narrowing, preliminary designs, weighted indices, and our final design narrowing. Problem statement, competition is hosted by AIC every year by, y'all know that. Each year they come out with new rules to keep universities from using the previous year's rule bridge in the current competition. It's a great competition because it challenges students to design a bridge or to meet certain requirement specifications that they will meet in their future profession as they have to deal with ASUCE or ASUCE when they're designing roads or bridges or any kind of structures. Most of our constraints that we came up with most of them were outlined in the rules. Had to pass all the dimensional templates, had to pass lateral load test during any point in the load testing, vertical or specifically lateral load test. Cannot exceed 3 inches in any point of deflection measurements. All the members have to fit in the boxes. Has to be constructed under 45 minutes, and the steel has to be magnetic. Criteria. Our selection criteria we came up with were 3 of them were the deflection, weight, and construction time. That came from the scoring equations in the rules package, and then also the cost it's going to cost us to fabricate it, and our ability to fabricate it. This is Austin's brainstorming. AP1, AP2 was the Bailey truss and the bowstring truss. They weren't picked because there are a lot of members in them, so it would take more time to build, more time to construct during the competition. AP3.
Take it away, Adam.
AP3 was a Warren truss, which has a lot of deflection compared to other trusses, but it also is easy to construct, so it's a trade-off. The K truss is pictured with an AP4. It was special because of its ability to resist moments at the center of the beam of the bridge. This is Tristan's first alternative solution. It's a simple arch truss design with 2D members. and this is Drew's. It was based on the winners from the 2018 competition. One of our main points of, I guess, research was just to look at people who had success in the past and kind of go use the stuff that they used. What's special about this is that it has a taper right here, so you basically have beam stacked upon beam to help with the internal moment. My first brainstorming solution was a simple beam bridge. Didn't have any truss support, but the idea with this one was just to reinforce the beams to compensate for this. This solution was basically copied from the University of Florida, the bridge they used in 2016. I thought that the thicker middle section would be advantageous.
So to get that down to a more reasonable number to actually do our modeling on, we set this up. We used those criteria that Tristan already mentioned and then kind of scored each one based on our expectations out of it, not out of actual analysis. So everything, we used AP3 as our base and gave that all zeros and then scored everything else based on how we expected to perform in comparison to that one. We picked that one because that was our Warren truss. It was the most base generic truss design. And so after we scored everything between -3 and +3 for all those criteria and added them up, it came out to be that the last four there, Tristan and I's design of both of Adam's came out at +1, and so they were the four that we moved forward with.
This is my design. It's basically just 2D members. What that means is they're relatively flat like a board. So they're easier to put together. 14, 16 gauge material. The 14 gauge material was just in the load rail here. 16 was everywhere else because load rail, the top here is a compression, so you need a thicker member there, and this is in tension, so steel's pretty strong in tension, so it didn't really matter there. The connection is basically just a lap connection, so the top is circular, so you can slide it in with a male-female connection because the top connection's, you're not going to put a bolt in it because it's compression, so you don't need it. So it's basically just male-female connection just for alignment. The bottom is a lap connection, so you just kind of slide it together, put a bolt in it, and you're done. The weight, this is with the 10% added from STAD, just for welds, nuts, and bolts and stuff like that. Construction time is 14.5 minutes. Best case and worst case deflection. The best case score, worst case score, 8 million, a little over 8 million for the worst case score. That's with six team members constructing. We plan on having 4 in the competition. So.
And then this is mine. Like Adam said, it has that taper in the middle. So right here along the middle, there's actually 2 beams that would have to be connected to each other, and then at the ends, it's just one. Then the truss is just a simple arch shape. It connects to the legs on each end, so the truss is actually shorter on that side there where it comes to that shorter span. And then there's just a few vertical members, and that's kind of based on previous year's bridges that performed well. The worst case score I got of this was 13 million, so I wasn't really very happy with that, so I did some optimizations on that. And I basically just ran a whole bunch of analysis for different beam types and truss types, and I made some pretty major overhauls and basically determined that it was best to just have the full double beam with no truss at all. Like the score just came out a lot better that way. It actually made it lighter, it made it deflect less, and it was faster to put together. And so all my scores improved by at least $3 million. And so with that, I came out to a best case of 8.7 and a worst case of 9.4 million.
I came up with 2 beam bridge designs. The first one is pictured here. It basically has a triangular section of beam and alternating cross bracing. The best case score was 9.6 million, and the worst case was 14.8. The next one was better because it had the moment of inertia of the cross section was, I guess, higher when you account for the amount of material that was used. The best case score was 10.5 million, and the worst case was 11.1.
So Austin took Adam's second preliminary or brainstorming idea, and his also used that taper there with a lot, but his truss was a lot bigger, had a lot more members in it, and was a little more box shaped. This did result in a lot higher weight. His weighed over 400 pounds and had more members, so it took 18 minutes to put together. But his deflection was pretty good, though. But his score still came out around 14 million for both the best and the worst case. So he optimized that by making the material in it a lot thinner, and he also removed a lot of the members in the truss. So he actually got his under 200 pounds, like cut over 200 pounds off his. So he was actually the only bridge out of the 4 that got under 200 pounds, could use that lower scoring formula. But deflection did increase a lot when he did that. Scores still increased overall for him, though, to under 10 million. So he did improve his scores a lot by getting the weight down, even though deflection did take a hit. And so then we weighted all of our criteria to determine how important they were for us when we were deciding which bridge we would select. So deflection, everyone was in agreement that that was the most important, and as all you know, it's worth $3.25 million an inch, so it was definitely the biggest part of the scoring formula this year. And I also did some comparisons from previous years on how each of those 3 that are involved in the scoring formula related to teams' overall scores. And deflection had something like an 80% correlation or something, so it was like very clearly the most important factor when determining how well a team scored. So we weighted that at 60%, and then time I think had something like a 30 or 40% correlation, so that didn't get rated as high, but still had some impact on how they scored, so we rated that at 25%. And weight didn't have much of an impact at all, but what we also saw was that a lot of the bridges that performed well last year didn't really have a lot of variance in weight. They all pretty much weighed within 20 pounds of about 200. And then originally we had cost and fabrication as 2 different criteria, but we combined those into one because they kind of went together. And also we didn't want either of them weighted that high because neither of them should be an issue. We should have no issue purchasing our material or building anything we want. So we combined those and gave it 5%. And then we scored each one based on actual analysis that you saw on the previous slides. Tristan's was used as the base here, so that got all the zeros. Mine had a little better construction time, it had fewer members, and was also better for cost and fabrication because there was no truss we had to construct, but it deflected a lot more and it weighed a lot more than Tristan's, so mine came out to a total of negative 0.95. Adams had a little better time, but worse deflection and weight as well, and was also a beam bridge, so he got the +1 on the last one, and he came out to a negative 1.2. And then Austin's was a little slower to put together and deflected a lot more, but weighed a little less than Tristan, so we got a +1 there. We got a 0 on cost and fabrication because they were both truss bridges, so there wasn't really any difference. So he got a negative 1.95. And since all 3 of them rated below 0 when we compared it to Tristan's, that's the one we ended up selecting. And so as we move forward now, we said that we would still consider bridges out of this class, which is why we are here today. And we're going to start our fabrication pretty early next semester so we can try to get everything put together and get our load test in and do our construction practice for competition, which is on March 29th in Ruston, Louisiana at Louisiana Tech. And we're hoping that we can take us back to nationals this year. We haven't been in, I guess, the last 2 years we've missed out, so we're going to try to get us back again. So if you have any questions for us, we'll take them. Paul?
So y'all haven't decided on a bridge between y'all 3 that y'all are going to choose? I guess y'all are still open to other options, but so you.
Well, yeah, I mean, Tristan's was one that was selected through that process, but I mean, if that's subject to change between now and then, if we determine there's something that we could add or change to make it better, and there probably will be some improvements before we actually start building on it.
How did yours do without a truss?
Mine?
Yeah.
No, I didn't. It wouldn't have done as well as Drew's was because his was pretty much the same as mine without the truss because he had just the 2D members with just cross bracing in the middle, but he had a taller member, so he had a bigger moment of inertia, so it would have scored better.
Questions? Okay, thank you.
The presentation was a lot better.
So I would like to thank you all guys for the good job that you did. I was scared a lot, okay, what you're gonna do. At the beginning you weren't promising at all, okay, but you improved, okay. So thank you a lot for putting the effort, okay, and working hard on it, okay. So I'm happy, okay.
That's all that matters. That's all that matters.
Yeah.
We hope you're happy.
If I'm happy, then
The grading goes
We're all happy.
yeah.
It's better grade.
Yeah, it's not better grade in terms of the 60 or like the number, but in terms of the letter grade, it will be better. So don't worry about that. There will be good curve. If I'm happy, there is good curve. If I'm not happy, there is no curve at all. Okay? So I'm happy. Okay? So thank you a lot for the effort that you put. Study well for the final exam. If you have any questions, you can come to my office. I don't know for the final. The last homework. Would you like me to waive it and just? I mean, I'm gonna post the homework and post the solution for it, so that you don't have to submit it. You just don't put any pressure on you that you have to study the material at a given time, right? Doing that way, you can study it any time and you have the solution, but there will be no credit for it. You don't have to submit it.
Could we turn it in for bonus?
No, because I will submit the solution. So
I want to do it.
When do you plan on submitting the solution?
the same time I submit the homework. So most probably today or tomorrow.
I'd rather do it for grade. I said I'd rather do it for grade.
When did we get our test, like our last test grade? When will we know what we got on the last test?
Yeah, I will for the second midterm exam. So for the second midterm exam, I'm planning on grading it today and tomorrow. So most probably by tomorrow, you're gonna know your grade. I'm gonna post them on that.
So be happy when you grade it.
I say you're gonna be.
Yeah. Will you go grade right now? Right now.
Are you giving us a decision to do the homework or not do it? Is it like a class decision whether we want to do it or not?
For grade.
It sounds like you made
It has to be, just the same thing for all the students.
Okay. So can we take a vote? Because I kind of want to do it. It help our grade, right? If you're good on it.
How much is your grade? Is our homework worth?
15%,
Like,
I think. That's
15%, right? The homework is 15%.
I don't need any more stress.
Okay, so
do it either way to practice.
I'm democratic, okay? My background is not from a democratic country, but I'm democratic, okay? So let's vote for it. So we have two options: either submit it on Wednesday, okay, and you take credit for it, okay, but that will put a pressure on you that you have to submit it by Wednesday. I know you might have finals, so that would be a distraction for you from your other finals. So one option is submitting it on Wednesday and take credit for it, okay? The other option is you don't submit it. I will post the homework and the solution for it, but you don't get credit. You don't submit the homework, okay? You just have the solutions for you to study, okay?
Can we do like a submission, and then after we submit it, you post the solution so we have it for like studying purposes, since our test is on Monday?
If you submit it on Wednesday, I will have the TA graded and I will give it to you by Friday morning, so you can study from it.
If we didn't submit a homework, when would we get the solutions? When would we post the solutions?
The same day I post the homework, I will post the solutions. So those are the two options, okay? Who wants to have the option to submit the homework on Wednesday?
As a grade or does it?
as a grade.
Okay. Okay. Who wants not to submit the homework, just post the solutions? Okay.
I saw my classes. I remember.
Sorry, Dylan.
That's 4 days of study.
2 hours leaving on like no more, please.
Majority of
Have a good one, Dr. Goff.
My bad.
Are you okay?